inks that we hardly can distinguish. So first of all, just to start again with the ink types, we have iron gold inks, which are products of a chemical reaction between iron two ions, and tannins with an addition of the binder. The most common iron gold inks, vitriolic iron gold inks, are produced with use of vitriol. Vitriol is as a source of iron ions. As we can see in this little photograph in the middle between the three photographs, we see a picture from a mine where vitriol was collected. We see all those different colors, and all those different colors represent the different metal sulfates which are present in such a vitriol. Comparison of such inks is therefore rather simple when we look at the elemental makeup of such an ink, because they differ based on those vitriols used. However, when we look at the non-vitriolic inks, the sources of iron are rather they contain no impurities. They are rather homogeneous. When the metallic iron is used, or other minerals such as iron phosphate within it, which I present in this slide, the makeup of such an ink is really relatively unique. First, let us look at this scary table of elements to the left. In the central part of it, we have I highlighted the most common vitriolic impurities that come from this salt, from vitriol. Manganese, cobalt, nickel, copper, and zinc. Those elements are very helpful for the comparison and determination of different types of vitriolic iron rings. We basically look at the ratio of those additions of those impurities to iron, which is always the main element, the crucial element for the production of iron gold. In vitriolic inks, as Professor Rabin already mentioned, we also have always sulfur, which comes from the sulfates, potassium, sometimes calcium. On the other side, we see that non-vitriolic inks contain basically just iron, sometimes some manganese as an impurity from other minerals, or from metallic iron. They can contain phosphorus if another salt was used for the production of an ink, and potassium from the binder or the tannins. I'll speak about tannins a bit further on in my presentation, but the sources of tannins were not always gallnuts, and now with the addition of another tool to our protocol, which Professor Rabin already mentioned, we can say a little bit more about that part, the organic part of the inks. You already received a little introduction to the XRF. XRF technique, which gives us information about elemental makeup of the material which we are studying. In principle, with XRF, we collect a spectrum, and in this spectrum, the energy informs us about the elements which are present, and the intensity of the signal gives us an idea about the abundance of the elements present in the sample. One of the tools which I love using, and I've been using a lot throughout my PhD and previous works, is an imaging XRF. Such a device moves the probe, as you can see in the image, over the area which one is investigating, and collects spectra, such as the one shown in the middle of the slide. And first of all, we determine the area which we want to scan with such a device. And each pixel in the area which we are scanning corresponds to one spectrum of such. And then, after a complete scan of the area is collected, we can display the whole area scanned as a map of elements. In this case, I'm displaying a relatively small map of elements, of two elements, of iron and zinc, which are mirroring the shape of the letter which was scanned in this fragment. Just to give you an idea how much time takes, it depends on the setup of the equipment. However, for the peak scan, which I was showing in this little video, we collected close to 750,000 spectra. So it's the points, and each point takes some time to collect. So it can be a couple of hours or dozens of hours, depending on the size of the area which comes. Here we have 5,000 spectra, which is a very, very short scan. Now, with this information, let us go back to the study of the God's name, which was already introduced by Nehemiah in his previous talk. Because with the use of the imaging XRF, we were really able to, first of all, strengthen the theory and give ground truth arguments for his hypothesis. First of all, we look at the two spectra, and this is the common the two spectra. On the top, the spectrum of the main ink, and on the bottom, the spectrum of the God's ink. Just a little spoiler, we found that the composition of the ink from the corrections and the God's names was the same. So let's just skip this for the further part of this presentation. The difference between those two spectra is very small. We see only a tiny little bit of copper present in the God's name, which is not present in the main ink, and the ratio between iron and zinc to iron was not really giving us much information. However, since we used an imaging XRF, we were able to produce maps of elements, and let us focus now on what we see here. When we look at the maps of iron and zinc, we basically see two mirrored images. Therefore, it doesn't give us much information. However, when we move to the map of calcium, we start to see some interesting patterns. We see two black areas where the signal of calcium is much lower, and now encircled in red, where the corrections which Nehemiah was interested in studying has been introduced. And in white, I highlighted the areas where the God's name was supposedly added. Now let's move to the map of copper. And in here, if we look at all those areas, we see that first of all, the God's names were definitely added to the text, and the same with the corrections. Now comparing all of those information together with the information about the same elemental makeup of the inks from God's names and corrections, we clearly see that those were first of all added, but more than that, the God's names were added together with corrections that's been introduced in those areas with the reduced amount of calcium encircled in red. Our hypothesis, it was Master Scribe who was correcting the scroll, and while correcting the scroll, also filling the missing names of God. In this case, clear example that those were added. However, this technique is also very helpful in studying inks which, as I showed in one of my previous slides, contain no significant vitriolic impurities which allow this kind of comparison. First, we look at the spectrum from not Elfus7, as it was in the previous case, but a scroll from a private Hungarian collection. And we see an example of vitriolic iron gold ink with zinc and some copper in it, a typical iron gold ink. Comparison of those is simple. However, when we look at vitriolic, non-vitriolic inks, which we found in this manuscript, it becomes problematic. We cannot really look at ratios of elements as those just contain iron. However, as we can see from this spectrum, we see that the ink in the middle, in comparison with the ink at the top, contains a different intensity or different amount of iron. This led us to proposing a method of comparing such inks of very uniform, similar composition. Here we're looking at a small crop out of one of the scans that we conducted on this Hungarian scroll. In the 4 lines numbered are here to help us follow what we revealed while using imaging XRF and using the way of presenting the data as heat maps. By heat maps, I mean that where the signal is stronger, the abundance of an element is higher, the color in the map displayed is warmer, and in contrast, when it's darker or colder, simply there is less of this element. If we look at the areas between the second and the third line, we clearly see that the calcium has been removed from the substrate, which fits well with different handwriting of those 2 lines, the second and the third line. However, if we look at the upper border of this area, we see that while removing those 2 lines, the scribe was not very much good. He removed portions of fragments, the tiny fragments of the letters from what is here labeled as the first line. Let us look now at the map of iron and whether it gives us more information about what's happened here. First of all, we clearly see that the ink from the second and the third line is written with an ink which contains a much higher abundance of iron. therefore, is displayed as much warmer, brighter colors. Especially, it's a striking example if we look at the third line where we see the letters appearing in red, and the red was set as the highest end of the spectrum of the abundance of this element in this case. Moreover, if we look at the fragments of letters in the first line, the fragments which I mentioned that were mistakenly erased together with the other lines, we can see how those fragments of letters were, in this case, added. More than that, when we look at the crowns, we see that all of those were also added to the existing text. And this way, even though the inks basically contain the same elemental makeup, we clearly see how those different stages of writing have been executed. This technique, in cases like this, requires a couple of hours to perform a scan. However, such a scan can be performed on a much bigger area with a slightly worse resolution. By resolution, I mean we select the size of the pixel at the time the device spends on collecting the information in such a pixel. In here, we see an area which covers, let's say, almost complete column and fragments of two other columns. In this big view, and the scan which took slightly more than 90 minutes, we see how we immediately see all the places which been corrected, highlighted in the heat map of iron. And also we see first of all we see the changes to the letters themselves, but we also see that some fragments have been heavily corrected. Let us look at a small area which is highlighted in red. What we see here, we see that the scribe who is correcting moved this one letter over here, and it's also mirrored in that, even though it's, first of all, this is a lower resolution scan, therefore we cannot read the letters which are here expressed in this black column. However, where the dark blue column, however, where the signal is higher in red, we clearly see how this message has been moved. More than that, we see how some fragments here of the text being corrected in the lowest line. Let us move to the final example of heat mapping helping in investigating text in the same case of the Hungarian scroll. When we compare the visible image with the image on the bottom, even though that the text looks really uniform, the hue or the color of the text is identical. The size of the letters, however, in the first and in the last line differs greatly. In this case, we focus on those. Let us first focus on those two portions of text. In the bottom, we see that at the end of the line, the intensity of the signal clearly corresponds with the fact that it was added later to the original text, which is expressed here in this dark red color. We also see that similarly crowns were added, and also this fragment in the lower line was definitely added. Let us move to the heat map of calcium to see what happened here. And in this case, the scribe was very precise in preparing this material for the corrections. Not only he removed the original writing, he was very peculiarly and meticulously following the shapes of letter. Therefore, now we can see the original layout of this text. How originally as a closed section was transformed into an open section. Since it's with this technique, we can resample and we can play with the way we collected the data. I'm going here to show you the same map as black and white image, where we can clearly follow what happened in this little passage. First, if we look at the line, at the first line on the top, we see how this encircled this marked in blue word was originally stretched here. We also see that the word in red box was originally here. More than that, if we follow the markings here, we see how a fragment of this letter was originally in the line in the middle, and in the end, the last section was simply stretched, was filling this whole fragment of the last line. with this slide, I'd like to move slightly from non-vitrolic inks towards the topic which was already mentioned by Professor Rabin in her talk, the presence of tannins, another crucial ingredient of inks, the organic part of inks. And as she already mentioned, very difficult to identify and to compare. First, let's have a look again on already familiar to you chart where we see those two different types of inks. As I mentioned, to source the acids, the phenols, the phenolic acids for the production of inks, basically two different historic sources could be used. First of all, we all know gallnuts, and the second one, the tree bark, usually the blackthorn tree bark. What is interesting, the compounds which we can identify in both slightly different. One is full of hydrolyzable tannins, and the other one is full of condensed tannins. But how can we investigate those? How can we identify the presence of such? Especially in the case of mixed inks, where we have carbon, which masks the evaluation and using the photography in different wavelengths to see the type of ink. When we look at the planting, this is an example of a planting from a mock-up that I prepared. We see that the tannins present in such an ink are quenching the fluorescence, blocking the fluorescence of the substrate. So this gives us a hint about the presence of such. However, it doesn't give us answer what kind of tannins or are they really present. For this, in the course of my PhD, I worked on an addition of another technique already mentioned by Professor Rabin, mass spectrometry. But more a solid analysis probe mass spectrometry, which is important because it's about a novel technique which allows a direct analysis of samples which can be collected and then measured in the laboratory without skipping the extraction steps. In this case, I'm showing a small fragment of a manuscript where I sampled the ink for the analysis with this device. If you look at the photograph of the whole fragment, we cannot see where it was sampled. However, if we look at the micrographs, this is 50 times magnification, we see that some ink was scratched from the upper part of the leather. However, this amount of the sample, when we look, it was very generous in this case. I collected much more material as it was samples we could collect as much as we wanted. And to conduct the real measurements, we only need a couple of those little drops of inks to get meaningful information. What kind of information? First of all, to do the measurements, one has to insert a probe with the little capillary on which one collects the sample. In principle, it could be possible to collect it directly from a manuscript, however, traveling with it would be very difficult. So for this, we propose a protocol in which we simply collect tiny bits of ink and close it between two panes of little glass, and then ship it or transport it ourselves to our laboratory. Then we insert it into the instrument. The whole analysis takes place, which is very fast, and we get the following information. In this case, we were able to identify gallic acid and pyrrolidol. The pyrrolidol is the smallest fragment of phenolic compounds that give us information, give us a hint that hydrolyzable tannins were used for production of such an ink, pointing towards the source of gallnuts for the preparation of this ink. On the other hand, in some other instances of inks and our mock-up samples, in cases of condensed tannins, which are very generously present in the tree bark, for instance, very common source of tannins for inks, we see catechol or other derivatives of condensed tannins. We can, using this method, differentiate among those two types of inks. Unfortunately, we cannot say what exactly tannins were introduced, as tannins degrade heavily, and yeah, we only see small fragments of those big molecules which were initially introduced there. To summarize my little presentation, I prepared a list of conclusions that I'd like to present to you. I hope I proved how imaging XRF is a powerful tool which can help answer different scholarly questions. Other than, I'd like to stress that not every Arundel ink is stressed on vitriol, as we know now from the results of our investigation. and also studies of mock-up samples. The micro-XRF and displaying the data as heat maps helps us in visualizing those fragments and sections that were corrected or written with inks of very similar composition. And finally, using the mass spectrometry technique, which I quickly mentioned at the end of my presentation, we can finally distinguish between type of tannins that was used for the production of ink. We are very thankful to all the people who participated in this work at different stages and at different parts of this research, and I thank you for your presence and attention today. Thank you.